Parallel plate capacitor. A parallel plate capacitor consists of two large plain parallel conducting plates separated by a small distance. Consider the area of plate is A. Charge on facing surface of one plate is Q and sigma is the surface charge density. Then sigma is equals to Q by A. This implies Q is equals to sigma A. Equation 1. Electric field between the plate is uniform and is given by E equals to sigma by epsilon naught, because we have E equals to E plus E minus equals to sigma by 2 epsilon naught plus sigma by 2 epsilon naught equals to sigma by epsilon naught. Hence potential difference between plate equals to dV equals to E dr equals to sigma epsilon naught sigma d by epsilon naught, that is dV equals to sigma d by epsilon naught, equation 2. Now by the definition of capacitance, C equals to Q by dV equals to sigma A by sigma d by epsilon naught. This implies C equals to epsilon naught A by d, which is independent of the charge given to the capacitor and depends on shape and size of the capacitor plates. Effect of dielectric on capacitance. Consider a parallel plate capacitor whose plates have magnitude of surface charge density sigma. The electric field between the plate is uniform and its value is E0 equals to sigma by epsilon naught. Now consider a dielectric is introduced between the plates. Polarized or bound charge appears on the surface of dielectric, which gives rise to induced field given by E in equals to sigma p by epsilon naught, equation 2. Now net electric field between the plate is given by E equals to E0 minus E in equals to sigma by epsilon naught minus sigma p by epsilon naught equals to sigma minus sigma p by epsilon naught, or E equals to sigma minus sigma p by epsilon naught, equation 3. So potential difference between the plates, dV equals to E into d, or dV equal to sigma minus sigma p into d by epsilon naught, equation 4. Now for a linear dielectric electrics, sigma minus sigma p proportional to sigma. This implies sigma minus sigma p equals to sigma by k, equation 5. Where k is a constant which is characteristics of the dielectrics. Using 5 in 4, we have dV equals to sigma d by k epsilon naught equals to q into d by a k epsilon naught, equation 6. Hence the capacitance of the capacitor with dielectrics, C equals to q by dV equals to q by qd by ak epsilon naught equals to epsilon naught ka by d, or C equals to epsilon naught ka by d equals to epsilon naught epsilon r a by d equals to epsilon a by d, where k equals to epsilon r equals to dielectric constant of the medium, that is dielectric, and epsilon equals to epsilon naught into k epsilon naught r, epsilon naught into epsilon r, permittivity of the medium or dielectrics. So we have epsilon r equals to k equals to epsilon by epsilon naught. For example, C air equals to C0 epsilon naught a by d, and C medium equals to C equals to epsilon r epsilon naught a by d equals to k epsilon naught a by d. 2 by 1 gives k epsilon naught a by d epsilon a by d equals to C by C f by C naught. This implies k equals to C by C naught, or epsilon r equals to C by C naught. Combination of capacitor.